Torch save. Description. Inputs. Model the ptorch model object you want to save. This object encapsulates the model's architecture layers, connections, etc., and its learned parameters, weights and biases. Filepath. The path where you want to save the model. This can be a file name or a directory path with the file name. The file extension is usually .pth or point. Saved model file. A file containing the model state dictionary parameters, architecture definition, and potentially other information, depending on the saving method used. Steps. The torch save function first serializes the model state dictionary, which holds the learned parameters, weights and biases of the model. It then writes the serialized data to the specified file path, creating the model file. Challenge 1. Saving a model with CUDA tensors. Sample use case. You trained your model on a GPU CUDA enabled and want to save it for later use. Fixes. Before saving, move the model to the CPU using model.cpu. This ensures that the saved model can be loaded on a device without a GPU. Challenge 2. Saving a model with custom objects. Sample use case. You have a custom class that you are using within your model, e.g., a custom loss function. Fixes. Define a custom getState and setState method within your custom class to handle serialization and deserialization of its attributes. Alternatively, consider using a pickle-compatible serialization format like DIL for saving and loading custom objects. Challenge 3. Saving a model with a complex architecture. Sample use case. Your model contains nested modules, custom layers, or complex data structures. Fixes. Ensure that all components of the model are pickle compatible or use a suitable serialization library like DIL. Use the torch save model state dict filepath approach to save only the model's parameters and load them later using model load state dict torch load file path. Torch load. Description. The torch load function is used to deserialize a ptorch object from a file. It reads data from a file, which was previously saved using torch save, and reconstructs the original object in memory. This object can be a model, a tensor, or any other ptorch data structure. Inputs. F. The path to the file containing the serialized object. This can be a string representing the file path or a file-like object, e.g., an open file. Map location optional. This parameter specifies the device CPU or GPU where the loaded object should be placed. If not specified, the object will be placed on the same device as the original object when it was saved. You can use CPU, CUDA, or a specific device index, e.g., CUDA 0. Outputs. Object. The deserialized object, reconstructed from the data in the file. The type of the returned object will be the same as the original object that was saved. Steps. Read the data from the specified file. Deserialize the data, reconstructing the original ptorch object. If a map location is specified, move the object to the desired device. Challenges and fixes. Challenge 1. Loading objects saved with an older ptorch version. Sample use case. A model was saved using ptorch 1.4 and you are trying to load it using ptorch 1.8. Fixes. Ensure you are using a ptorch version that is compatible with the version used to save the file. If you are using a newer version, try loading the object with the pickle module. Use the load from stateDict method to load the model, followed by load stateDict to ensure compatibility with older versions. Challenge 2. Loading objects saved on a different device. Sample use case. A model was saved on a GPU. but you are trying to load it on a CPU. Fixes. Use the map location parameter to specify the desired device. If you don't have access to the original device, e.g., a GPU, you can load the object on the CPU and then use Tokuda to move it to the desired device. Challenge 3 loading objects saved with a different data type. Sample use case: a tensor was saved as torch, float 64. But you are trying to load it as torch, float 32. Fixes. Ensure that the data type of the object you are loading matches the data type used when the object was saved. Cast the loaded object to the desired data type using type. Challenge 4 loading objects saved using a custom class. Sample use case: a custom class, e.g., my dataset was used in the saved object, but you don't have access to that class definition in your current code. Fixes. Ensure that the custom class is defined in your code before attempting to load the object. You may need to re-implement the custom class if you don't have access to the original definition. YAML. Torch getNum threads. Description: this function returns the number of threads used for parallel computation in PTorch. This value is set by the torch setNum threads function or automatically determined by PTorch based on system resources. Inputs. None. This function does not take any input arguments. Outputs. Number of threads: an integer representing the number of threads currently used for parallel computations within PTorch. Steps. Query system: PTorch internally queries the system's available resources such as CPU cores and determines a default number of threads to utilize. Return value: the function retrieves and returns the currently set number of threads for parallel computations. Challenges and fixes. Challenge 1: incorrect thread count. Sometimes the returned thread count might not accurately reflect the actual number of threads used by PTorch. Sample use case that resulted in challenge 1: setting the thread count manually to a value higher then the available cause might result in an inaccurate count, as the actual number of threads used could be capped by the system's limitations. Fixes to challenge 1: verify that the set thread count is within the limits of the system's available resources. Challenge 2: oversubscription. Using a large number of threads can lead to oversubscription, where multiple threads compete for the same resources, leading to performance degradation. Sample use case that resulted in challenge 2: setting the thread count to a high value on a system with limited resources can cause oversubscription, resulting in slower execution times. Fixes to challenge 2: experimentally determine the optimal thread count for your specific hardware and workload. It's often best to start with a lower thread count and gradually increase it until you find the best balance between performance and resource utilization. Torch setNum threads. Description. The torch setNum threads function sets the number of threads used for parallel operations in PTorch. It controls the number of threads available for operations like parallel data loading and computation. Inputs. Num threads: an integer representing the desired number of threads. Outputs. None. Steps. The function takes the desired number of threads as an argument. It sets the environment variable OMP and UMTHREADS to the specified value. This variable controls the number of threads used by OpenMP, a multi-threading library commonly used in PTorch. Challenges and fixes. Challenge 1: setting an excessively high number of threads can lead to performance degradation due to excessive thread creation and context switching overhead. Sample use case: setting torch setNum threads 100 on a machine with only 4 cores might result in significant overhead. Fixes. Set the number of threads to a reasonable value that aligns with the number of available CPU cores. Generally, setting it to the number of cores or slightly higher, e.g. twice the number of cores, is a good starting point. Challenge 2: the number of threads set might not always be the exact number used by PTorch. Especially when dealing with multi-threaded operations that involve other libraries like NumPy or CUDA. Sample use case: setting torch, setnum threads 4 might not result in exactly 4 threads being utilized by PTorch if the underlying libraries have their own thread management. Fixes: use profiling tools like Torch Profiler or cProfile to measure actual thread utilization and adjust the torch setnum threads value accordingly. For optimal performance, consider using the Torch multiprocessing module for parallel operations, especially when dealing with computationally intensive tasks that can leverage multiple CPU cores. Ensure that the libraries you use are configured to work well with PTorch threading model. YAML. Torch getnum interop threads. Description. Inputs: none. Number of threads used by PTorch for interoperability with other libraries. Steps: this function queries the underlying C implementation of PTorch to determine the number of threads currently allocated for interoperability tasks. Challenge 1: determining the optimal number of threads for interoperability can be challenging and dependent on hardware and workload. Sample use case that resulted in challenge 1: a user might experience performance issues when interacting with a library that uses a different threading model than PTorch, resulting in contention and slowdowns. Fixes to challenge 1: carefully assess the performance characteristics of the library and hardware being used. Experiment with different thread counts using Torch setnum interop threads to find the optimal value. Challenge 2: incorrectly setting the number of interoperability threads can lead to resource exhaustion or performance degradation. Sample use case that resulted in challenge 2: setting the number of interoperability threads too high can lead to excessive CPU usage and contention, impacting overall performance. Fixes to challenge 2: start with a reasonable number of threads based on the available cores and the expected workload. Monitor CPU usage and adjust the thread count accordingly. Torch setnum interop threads. Description: the Torch setnum interop threads function is used to control the number of threads used by PTorch for interoperability with other libraries, such as NumPy and SciPy. This function allows you to fine-tune the performance of your PTorch applications when interacting with these libraries. Inputs: num threads, an integer representing the desired number of threads to be used for interoperability. If you want to use all available CPU cores, set num threads to 0. Outputs: none. This function does not return any value. Steps: the function sets the number of threads to be used for interoperability operations, such as transferring data between PTorch tensors and NumPy arrays. The specified number of threads will be used by PTorch for interoperability tasks, potentially improving performance. Challenges and fixes. Challenge 1: oversubscription. Using too many threads for interoperability might lead to oversubscription of CPU resources, causing performance degradation due to context switching overhead. Sample use case that resulted in challenge 1: setting num threads to a large number, exceeding the available CPU cores. Fixes to challenge 1: choose a reasonable num threads value that is smaller than or equal to the number of available CPU cores. Monitor CPU usage and adjust num threads accordingly. Challenge 2: underutilization. Setting num threads to a low value might not fully utilize available CPU resources, leading to suboptimal performance. Sample use case that resulted in challenge 2 setting num threads to 1. When multiple cores are available. Fixes to challenge 2 increase num threads to leverage the available CPU cores. Start with a value equal to the number of CPU cores and adjust based on performance measurements.